Good morning, good afternoon, or good evening. Hope you're doing well today, folks. Welcome back to Unit 6, Energy. Today we are finishing up the unit with Lesson 6.3, which is all about mechanical energy. If you remember, we discussed mechanical energy briefly the other day. We said mechanical energy is energy associated with movement and position. So we can break mechanical energy down into two smaller pieces, which we call kinetic and potential energy. Now, kinetic energy is abbreviated by a capital K, which makes sense, and potential energy is abbreviated with a capital U, which makes no sense at all. But that's the way it is. Kinetic energy is specifically energy of movement. If you are moving, you have kinetic energy. The faster you're moving, the more kinetic energy you have. Potential energy is energy of position. So for example, if you climb to the top of a ladder, you have more potential energy with respect to the ground, and this is due to the pull of gravity. The formula for kinetic energy is 1/2 mass times velocity squared. So there's a lot going on there, so pay careful attention whenever you're calculating kinetic energy. You have to multiply the mass by 1/2 or simply divide by 2, which is the same thing, and then you have to square the velocity. Don't forget to do that part. Gravitational potential energy, that is, your potential energy is caused by gravity, is given by your mass multiplied by the acceleration due to gravity multiplied by your height, and your height is always relative to some reference point. Now normally we would use the ground as height 0, and then your height above the ground is the number you would plug in here. We say your height above the ground, we don't mean how tall you are. We mean how far you are physically removed from the ground. So for example, if you're in an airplane or climb a ladder, that's the height that we're talking about. There are two types of forces to know about when we're talking about mechanical energy. One is called a conservative force. And if you look at the word conservative, you get what it does. It conserves mechanical energy. So a conservative force is a force that does not cause a change to the overall mechanical energy. Gravity is a conservative force. When an object is free falling, it is losing potential energy because it's losing height, but at the same time it is gaining kinetic energy because it's speeding up. And the amount of kinetic energy that it gains is exactly equal to the amount of potential energy that it loses. So we say gravity is a conservative force because the sum of these two forces stays the same. A non-conservative force is a force that causes the overall mechanical energy to decrease. Friction would be an example of a non-conservative force. And we'll take a look at some examples of this. Let's start with gravity. We have this red ball here. It is going to fall from a height. As it falls, we will see its kinetic energy increasing along with its speed. Meanwhile, its potential energy will decrease with its height. But the sum of these two energies, the mechanical energy, will remain constant. So there we go. We freeze the action just as the ball reaches the bottom of this ruler. So you can see that at this point, all of the potential energy with respect to the bottom of the ruler is gone, has been converted into kinetic energy, but the sum, the mechanical energy, never changed. Now let's look at an example of a non-conservative force like friction. We're going to have this box sliding across the tabletop. It has no potential energy with respect to the tabletop because its height is 0. But it's going to start off with kinetic energy because it's moving, and then friction will cause it to grind to a halt. As the kinetic energy decreases without a corresponding increase in potential energy, the mechanical energy will also decrease. So that's why we say friction is a non-conservative force. The total amount of mechanical energy decreased as the box slid across the tabletop and came to a stop due to friction. Now, in real-life situations, there are both conservative and non-conservative forces at work. Consider riding a roller coaster. The chain that pulls you up the first hill is adding mechanical energy. So once you get to the top and you go over the top hill, gravity pulls you down, which causes you to lose potential energy but gain kinetic energy. Remember, gravity is a conservative force. And if there were no friction at all, then you would go through the entire ride with its total amount of mechanical energy that you started with at the top of the first lift hill. However, there is friction, and so in reality, the roller coaster is slowly losing mechanical energy for the entire time that it's running around the track. And when you design a roller coaster in real life, you have to take that into account. So no hill after the first one, no hill can be as tall as the first hill, because every hill or loop or corkscrew that the roller coaster goes through, it's lost some of its mechanical energy. And if you make a hill that's taller than the first one, the roller coaster will not be able to get up that hill just based on its mechanical energy. So let's take a look at this skill practice question. What is the kinetic energy of a 70 kilogram jogger moving at 5.0 meters per second? We're going to simply use the kinetic energy formula. K is equal to half the mass times the velocity squared. This is a plug and chug type problem. There's no manipulation or logic required. We simply plug in the numbers and crank out an answer. So the mass of the jogger is 70 kilograms. I'll plug that in for m. And then the jogger's velocity, jogger's velocity is 5.0 meters per second. So I'll plug that in for v. Don't forget you must square the velocity. Very, very important. All right, so let's solve. Half the mass is 35 kilograms. Half of 70 is 35. And 5.0 meters per second quantity squared is going to be 25, two significant figures, meters squared per second squared. Then we will multiply these two numbers together. 35 times 25 is going to give you, 875 in your calculator, but we're only allowed two significant figures, so you either have to round it to 880 without a decimal, or you can just write 8.8 times 10 to the second. And you have kilograms times meter squared per second squared, which is a joule. All forms of energy are measured in joules, including kinetic energy. All right, here we have another sort of plug and chug problem. This time we're solving for gravitational potential energy instead of kinetic energy. What is the gravitational potential energy of a 1.5 kilogram apple pie perched on a windowsill 2.0 meters above the ground? See, we will use the formula for gravitational potential energy, which is mass times gravity times height. And plugging in the numbers, the mass of the apple pie is 1.5 kilograms. We assume that this apple pie was baked right here on good old planet Earth, so we will use 9.81 meters per second squared, the gravity, and the height of the apple pie is 2.0 meters. All you have to do is just multiply those three numbers together, round to two significant figures, and the calculator is going to give you 29.43. We'll just round that off to 29 joules. This apple pie has 29 joules of potential energy. If it were to fall off the windowsill, then when it hit the ground, it would have no potential energy, but it would have 29 joules of kinetic energy, assuming that there was no air resistance and it didn't lose any mechanical energy on the way down. In reality, it would lose a little bit of mechanical energy, but if we ignore air resistance, then this is also the number that tells us how much kinetic energy the apple pie would have if it fell off the windowsill and hit the ground. Let's take a look at one more skill practice problem. Now, this is a more complicated problem than the previous ones, but it's using the same concepts. This is something we can figure out. Marble enters a curved tube at 2.00 meters per second. So it's going to enter the tube here, it's going to roll down and then back up, and then it's going to come out the end here. If we neglect friction, how fast is the marble moving when it leaves the end of the tube? Now, I know this looks really scary, like it's got all these bends and stuff. What's going to happen to its velocity? Here's the thing. We don't have to worry about any of that, right? We know how much, we can figure out how much kinetic energy the marble has going in here, and it has a certain amount of potential energy. And if there's no friction inside the tube, then the total amount of energy is going to stay the same, which means that when the marble leaves the tube, its kinetic plus potential energy is exactly the same as its kinetic plus potential energy when it entered the tube. So we'll use that information to kind of help us. We'll say that E stands for mechanical energy, is equal to EF. So the amount of mechanical energy going in is equal to the mechanical energy coming out. Now remember, mechanical energy is equal to the sum of kinetic and potential energy. So we will say that the kinetic energy of the marble going in plus its potential energy going in is exactly equal to its kinetic energy coming out plus its potential energy out. We know that the kinetic energy of the marble is given by 1/2 the mass times the velocity, call that VI squared. And its potential energy is equal to mass times gravity times height. We'll call that initial height. The kinetic energy of the marble coming out is equal to 1/2 its mass times its final velocity squared, and that's actually the number that we're looking for, is the final velocity, plus its mass times gravity times its final height. Now you'll probably notice that the mass term appears in all four, or the mass appears in all four terms, which means that we can actually factor it out. So I did not give you the mass of the marble because if there's no friction and no other non-conservative forces, the mass of the marble really doesn't matter at all. So we can just factor that out. It could be a simple little 1 gram marble. It could weigh a ton. It doesn't really matter. So we are left with 1/2 initial velocity squared. The initial velocity is 4.00 meters per second. Let's square that. Don't forget to square it. Plus gravity times the initial height. Gravity is 9.81 meters per second squared. Times the initial height. The marble is initially 1/2 meter above the tabletop. So we'll use that as our reference height. 50 meters. Equals 1/2 the final velocity squared. We do not know what the final velocity is, so we'll just leave it as VF for right now. Plus, gravity is still 9.81. Now we can't factor out gravity because it doesn't appear in all of the terms. It only appears in 2 of the terms. So if we tried to factor it out, we would run into some problems. Multiplied by the marble's final height, the marble winds up 0.15 meters above the table. So we've got everything we need, and yeah, it looks pretty complicated, but we're going to simplify it down. We're going to get the answer that we need. All right, so first of all, I just made a mistake, didn't I? I put in, you're screaming at the screen like, no, it's 2 meters per second. Yes, it is, okay? I got ahead of myself. I went ahead and squared it prematurely. Don't do that. All right, so 1/2 times 2 squared. Well, 2 squared is 4, and then 1/2 of 4, we're back down to 2. But we're going to have 2.00 meters squared per second squared, because you don't just square the number, you also square the unit. So once again, we squared 2, which 2 times 2 is 4, but then we took 1/2 of 4, so we're back down to 2, but our units have been squared. Plus 9.81 times 0.50, and if you punch that into the calculator, you're going to get 4.91. Now technically I should round it to 2 sig figs, but because this is early in a multi-step problem, I'm going to keep 1 additional sig fig. Just remember, when we get to the end, we're going to have to round down to 2 significant figures. Got meters times meters per second squared, so we're going to wind up with meters squared per second squared, which is good. Whenever we're adding 2 numbers, they have to have the same units, or they would not be able to add. On the other side, we've still got 1/2 times VF squared plus 9.81 times 0.15. Again, I'm going to do the trick of keeping 1 additional significant figure, so that's going to be 1.47 meters squared per second squared, because we have meters times meters per second squared. All right, now we will add these 2 numbers on the left side, so 2.00 plus 4.91 gives us 6.91 meters squared per second squared. And on the right-hand side, well, nothing really changes there yet. We're about to make some changes. Now we will subtract 1.47 from both sides. I'm going to come up here to give myself a little bit more space. 6.91 minus 1.47 gives us 5.44 meters squared per second squared. Left-hand side. On the right-hand side, we have 1/2 VF squared. We're going to multiply both sides by 2, which is going to give us 10.88 meters squared per second squared. And on the right-hand side, we have VF squared. We take the square root of both sides, and now we're going to finally round it down to 2 significant figures, and we'll get 3.3 meters per second on the left. We take the square root of meters squared per second squared, we get meters per second. And on the right, we have VF, which means we have reached our final answer. So if the marble enters this side moving at 2 meters per second, it will exit this side moving at 3.3 meters per second. And that is going to bring us to the end of our unit or our lesson on mechanical energy, and it also brings us to the end of the unit on energy and work. As always, there will be a Google Doc with a few questions about this chapter or about this lesson, so please do check that out. Make sure you complete those activities and make sure you turn them in when you're done. Join me tomorrow when we'll be starting a brand new unit. Until then, take care, stay safe, keep washing your hands. Talk to you tomorrow. Bye.